Hi, I'm Samin. In this assignment, we loaded and played with CO2 data, which is collected at the Manuel Loa Observatory over the last 60 years. We also used El Nino Index dataset that records the temperature changes due to the El Nino effect. We tried to apply some of the methods we learned in the class on these datasets. The first thing that we needed to do was to import pandas, numpy, and matplotlib libraries. For the first question, we were asked to introduce a new column called date on our given data frame that combines the year and the month into one column. To do this, we use pd.toDateTime function, which is a pandas built-in function and accepts a data frame with three columns, month, day, and year as its first argument, and outputs a data frame with a single column corresponding to that date. First, we created a column called day in the data frame df and set it equal to 1 for all rows, as you can see in this first block of code. And the next block of code, we selected the three columns month, day, and year from df and passed the result to df.toDateTime function. Next, we created a new column date in the df data frame and set it equal to our output of pd.toDateTime to create a new column corresponding to that date. Since now on, we only care about the column date, CO2, and trend, we selected these columns and discarded everything else, as you can see in this block of code. In the next step, we set the index to date using df.setIndex. Then we plotted the data using df.plot function, as you can see in this figure. It is given that the dataset uses minus 99.9 in the CO2 column to denote the missing data. So we set these values to none instead, as you can see in this figure. And as you can see in this block of code, using a lock attribute, which accesses a group of rows and columns by labels. Then we used the series.interpolate function to fill the missing data with path, and then we plotted the data again, which is shown in the following figure, and saved it as a qsn1.png. And lastly, we plotted only the data since 2008 by selecting only the rows after 2008, as can be seen in the following figure. Now we're able to see the seasonal variation more clearly. In the second question, we were asked to fit our data with a curve of specific functional form. First of all, we created a column called float time to represent the floating point value of the year, and to do this, we used df.indexMonth and df.index.year to create the formula that represents time as a decimal number of years by adding the df.index.year to 1 minus 1 over df.indexMonth and making it equal to our float time column. Next, we created a function to represent the curve that we will use to fit the data, which represents the following mathematical function. To do this, we use an exponential curve using math library and created our function with four parameters t, a, b, and c, which returns the mathematical formula. And next, we created another function called model curve, which takes again four parameters and returns mp.asArray function, which is to convert the input to an array, as can be seen in this following block of code. Next, we use the scipy.optimize library to fit this curve to the trend column in the dataset. To do this, we used opt.curveFit function, which takes our model curve as the first parameter, the float time column as the second parameter, and the trend column as the third parameter. We can think of this as a sort of manual fitting step before we refine our guess using scipy. In the next step, we created a new column called curve. We created a new column called curve fit and stored the curve which we previously fit, and then we plotted both of these fitted curve values and the CO2 trend values in the same plot, as can be seen in this following figure, and saved it using a fig.savefig function. In the third question, we were asked to find out when will it cross 500 ppm according to our naive curve model, in which we used SciPy to optimize packages root finding functions to find when will your curve cross the 500 ppm threshold mark. We did this using opt.root functionality that takes our curve model as its first parameter and adds 1900 to our formula as its second parameter, and then the three ABC parameters as its third parameter. Next, we plotted the CO2 trend along with the prediction values until the year it would reach 500 ppm. We did this by plotting our curve model and turning our input to array using np.asArray functionality. And lastly, we printed the legend for our plot and saved the figure using fig.savefig functionality. In the fourth question, we were asked to use the curve fit that we created earlier to abstract the general or increasing trend we see from the CO2 levels. The dataset was downloaded in this section by running the cell. First, we stored the differences between the trend column and curve fit column in a column called CO2 variation, which shows how the CO2 level deviated from the curve model in a particular month, and plotted the result by giving it a label and a legend. Then we found a common set of datasets between the datasets DF and ONI DF to perform the analysis on. We did this by first making it equal to ONI DF and then resetting the indexes of DF using reset index function, and then dropping the index column using drop function, and then storing the aligned CO2 level data frame in a variable called DF sub, and the ONI values data frame in a variable called ONI df sub. The output below shows the same start and end dates. In the next step, we extracted the values into NumPy arrays to use for regression as x and y. Then we trained a linear regression model to predict the CO2 variations using ONI values. To do this, we wrote a function called featured that takes two parameters x and d and returns a matrix of d columns where each column is a time-shifted version of x. First, we created a last value which is assigned to d and an empty list and an initial value that is set to 0. Then, using the while loop, we appended the TMP to our empty list whenever the length of the x is greater than or equal to the last value, and then we return the array version of our new array. After that, we printed the input and output values, and we can observe that they are the same with the expected input and output values, like this. In the next step, we used d is equal to 12 to featurize the x values and train a linear regression model to predict y. First, we imported the NumPy and sklearn libraries and used our previously created featurized function to make d equal to 12. Then we took the first 11 indexes of our y parameters and used it in our linear regression model. In the next step, we stored the regression prediction. To do this, we created an empty list of zeros and extended our regression model prediction to it. And then we performed the storage operation in column called ONI regression and plotted both the ONI regression and CO2 variation columns in the sample plot, as you can see in this following figure. And lastly, in order to confirm that the prediction is better than the later years after 1995, we plotted from 1995 onwards and recomputed the Pearson coefficient for this time period. We then saved the figure as qsn4.png using fig.savefig function. Thank you so much for listening.